Heads up, I don't have access to the chat because I have both screens with the presentation. So uh, just unmute and say something if you feel like it's worth stopping me for whatever reason. And disclaimer now from my side, I know that I can talk really fast. I already said it before. So if it gets so fast that it's hard to understand, please stop me. Just, I have no problem at all with that. But now let's start with the real thing. So yeah, as Adi mentioned, the main topic today is privacy preserving AI, and we are focusing a lot on homomorphic encryption. If you're not familiar with it, don't worry. I will go through all of the basics. I will explain what it is and so on. So we will start a little slow, but bear with me. We will get somewhere. Do not feel like we are just getting through the basics. Hopefully it's gonna be interesting for all of you. So first thing, in the obvious, I already warned you that it's going to start being pretty basic, is that AI heavily relies on data. We use it for everything. It doesn't matter what you're doing, either for training, validation, like cross-validation, right? When you want to take a subset and check if it's actually accurate on how it's getting. Well, let's go with that. Let's go back to the basics. Either you are testing, maybe you are fine-tuning. You have all of this awesome trained model, and now you want to add more data now to make it to fit your needs a little better. It doesn't matter what it is. You're always looking for more data. But there is something to be warned about when it comes to that, and it's that confidentiality can always be a problem. Because you can be adding a lot of confidential information without noticing, or you maybe know it and you don't care. You can be adding medical records, financial data, I mean, personal communications. We have all seen how WhatsApp, it's like hey, I want to buy some new headphones, and suddenly Facebook and Instagram, they are like all of the ads. Those are private conversations at the end of the day. And of course, sensitive personal information. Could it be your sexual orientation, about your religion, about political opinions? I mean, some of these might not seem too like important because of the state of the world and how open things are nowadays, but depending on where you are, all of these can be important. And it's really easy to fall into the pitfall of saying, oh, but I need all of this data because I'm making this life-changing artificial intelligence system that is going to change your life. It is for a better what can I say, for a better experience and make the world better and blah, blah, blah. It doesn't matter. It's sensitive information and you need to do something about it. And that's what brings encryption, right? I mean, if you listen to all of the previous things that I said, you might be thinking, well, encrypted and that's all. Because that's what encryption does. You take some sensitive private information that you want to be able to see again in the future. Well, you encrypt it. You get some random characters that now don't have any meaning. Do you want to see it again? You decrypt it. Yeah, that's fairly similar to what we do nowadays. If we if we look at an example of how we go through a system right now, it is really similar to this. You have your plain text input, call it your message that you're sending on a chat, call it the values on a form that you're filling because, I don't know, you're checking your credit score or whatever, and you are going to encrypt that either via SSL or any type of secure communication channel. It gets sent to the server. It gets decrypted because it needs to know what is in there, right? In order to be able to process it. It does whatever magic it needs to do with your data. It encrypts it again, sends it to you, and boom. Now you can decrypt it and you get your response with whatever you're looking for. It's fairly good, but actually we can do better. There are some flaws on this model, and the first one is that, yes, you're encrypting data on transit, but you need to decrypt that in order to be able to process it. When you decrypt that data, now you're opening yourself to some possibilities. Sorry about that. For example, decrypted data can fall as a victim of side channel attacks. You can also fall into a malicious party just injecting code and doing something with your plain text data when you're on that particular stage. And we even have vulnerabilities like some of you might remember Heartbleed, like, what was it? 14, 15 years ago, I think? Even less, I think. And what was Heartbleed doing? It was pretty much allowing you to send a malformed request. Now you say, hey, I'm sending 5 MB of data. You were actually sending 500 kilobytes. And it was allowing it to retrieve the rest of the data from memory. And with that, you were retrieving cryptographic keys, decrypted values, a lot of data that was in memory. And I mean, this is really similar to this. Yes, you were encrypting data. Yes, you had your keys in a safe location like a key vault or whatever. Yet you could get compromised. So yeah, it's not perfect. And that's when homomorphic encryption comes into play, because we can do it a little better. Now, unlike the first example, where we had to decrypt the data on the server, cloud service, whatever thing you're using, now we take your input, you encrypt it, you send it to the server. Let's use the term server for the rest of the presentation, just to avoid going too deep into the type of system that is processing that. So it gets into your server, you process it, you never decrypt your data. It is encrypted. You process encrypted data, you can understand a way to process that encrypted data, produce an encrypted output, you send it, and now only the owner of the key, it can be many, right? But the one with the key can decrypt it. This is really powerful because now the system never learned anything about your information. I mean, you could be adding some weird symptoms that maybe you don't want anyone to know about on a system that you want to know what disease you might have, and the system never learned anything about it. And that's the beauty of this. Now, what is it doing? I mean, how does it work? I will be simplifying things a lot, so if someone here is a cryptographer, please don't hate me. I will try just to keep things simple because I'm not a cryptographer. But the first thing is that it creates encrypted values that allow, let's say, homomorphic computations to be performed. This pretty much says, I have two encrypted values, just for the sake of the example, and now I can say, for example, 5 encrypted times 3 encrypted, it's able to calculate that this is a 15 encrypted. And you get the encrypted 15, you decrypt it, and boom, it's 15. And the system doesn't know what it is. It is like, I got this weird thing and this weird thing, I multiplied, got this even weirder thing. I don't know what it is. There you go. I guess that you care about the result. I don't know what it is. 1 second. Sorry, had to clear my throat. So I actually already said everything, right? It's you have two encrypted values that you can perform computation on them. You get an encrypted result. As a beauty of this, you also are allowed to do multi-party computation so that you can run into more complex scenarios. We are going to be looking at little of it later during the presentation, but that's pretty much what it does. Now, if we look into a more practical example, yet now with some names on it and not just imaginary numbers floating all over the place, we can use a healthcare industry as an example. So you, as a patient, are filling an online form with some symptoms that you have, and you are like, hey, you know what? I have a headache and my eyes hurt, and maybe I'm coughing with blood. I don't know. I'm just getting a little drastic here, right? But the thing is, you have this, it gets encrypted, it gets sent to the server, and now the server is computing, it's doing whatever magic it needs to do, but unencrypted data, it never learns your symptoms. It does whatever it needs to do. It says, hey, here's the response. It is also encrypted. There you have it. And maybe you get it, I don't know, you can get an encrypted document to download, or you connect to a portal, who cares? And you are the one with the key. And only you can see the potential diseases that you have. Or maybe you want the doctor to have that power. Sure, doctor, here is my key. Please decrypt it and look at it and tell me how bad it is. The thing is, the system never learned anything. The system can get compromised, many things can happen, yet it never learned anything. And yes, there might be other attacks that can affect it, but at least it's not getting as many attack vectors as it happened on the original example that I showed at the beginning. Now, I can say homomorphic encryption, but it's not a single one. It's not like, oh, it's only this and nothing else exists. Actually, there are three types in general to refers to homomorphic encryption. First one is partially homomorphic encryption, and it means that it's limited on the type of operations that it can, on the amount of on the type, sorry, of operations that it can perform. For example, RSA as an algorithm that it's partially homomorphic because it allows you to perform multiplication out of the box. I mean, with RSA, the encrypted values, you can perform a homomorphic multiplication, but only that. You're limited. You do not have all of the features that you could. So that's why it's partially. Then you have somewhat homomorphic encryption. This one is more powerful when it comes to what it can do, because this one supports addition and multiplication, which is really powerful, and we will see why in a few minutes. But the problem is that it has a finite number of operations. So you can be like 2 times 5 equals 10, 5 times 3 equals 30, and you keep going over, and suddenly it is like, yeah, you know what? This is getting hard to understand. I'm not able to keep track of the values anymore, and I might not give you an accurate result. So this is the point where we should stop, or you can keep moving forward, but now you're taking the risk of that not being accurate. That's somewhat homomorphic encryption. And then you have fully homomorphic encryption, which pretty much allows you to do multiplication, addition, but now an infinite amount of times. Well, infinite, and we will see why in a few. But now this is the real one that we care about for most of our examples, because we want to be able to do that as many times as we want. When it comes to artificial intelligence, we are performing millions and millions and millions of operations in order to predict and pretty much train and do whatever we want. So we want to have as many iterations as we can. And now you might be wondering, okay, so you're telling me multiplication and addition. I don't care about that. I want to do complex stuff. I want to do prediction. I want to get my LLM responding with the most accurate answer. Yeah, well, math is the base of all of artificial intelligence algorithms. I mean, you can see this example, a classic example of like logistic regression, neural networks. You are doing a bunch of matrix multiplication and addition and multi-layer arrays and blah, blah, blah. So it is important. Do not think that the focus of the presentation will be, oh, you can multiply two numbers in an encrypted way. That's amazing. No, it's way more complex than that. So please do not get fooled by thinking into that. And now the real question is how secure it is. Because yeah, it sounds awesome. I can perform computation on two values and get something that it can be understood by the end user. It might have some weakness, right? It's like, it is at least not as safe as what we use nowadays. And the answer is no. Actually, it's fairly good. I mean, same as nowadays algorithms, is quantum resistant, at least for today's standards. Works based on a complex mathematical problem, just like the others do. It's based on zero knowledge proof, so it's fairly strong. It's not like you're reducing the security of your system or doing something, weakening your system for the sake of having this type of properties. But not everything is beautiful here. Because if it is as perfect as I'm saying that it is, then why is it not being used everywhere? Why is it not the norm nowadays that everyone are using this? And the problem is that it is a complex solution for a complex problem, and that makes it really slow. Like really, really slow, and we are gonna go deeper later into that part. But the good news is that it has been getting better over the years. I mean, if we go back to when homomorphic encryption was defined, it was like back in the 80s, and it just didn't get that much hype, to call it in some way. If we go back during the last 15 years, we can see on this chart that it has been getting way better. I'm sorry that I couldn't get data for this year. It is just one of the only sources that I found from a good source, in this case, Dr. Christine Lauter. But it has been getting way faster. So yeah, maybe it is slow, pretty slow, but it has been getting way, way, way faster as well. And with that, it is also a growing market. There are more companies interested on it. There are more projects focusing on leveraging homomorphic encryption. And of course, when you talk about how this keeps growing and there are more entities interested on it, always brings up specialized hardware. And one of the things that we are looking, well, they are looking, I'm not into it, right now is into the ASICs for next year. So that will be the first generation of hardware acceleration when it comes to homomorphic encryption. I like this example because this is not about homomorphic encryption. This is about AES once Intel added the specialized set of instruction on their CPUs. Some of you might remember that 15 years ago, if you were encrypting data, you were like, oh no, you need to be careful. I mean, you are adding extra overhead. If you're encrypting something, you are making your application slower, and now you need to decrypt it. And you were all crazy about it because it was performance, performance, performance all over the place. And it was real, right? I mean, if we compare 15 years ago's computational resources compared to nowadays, but then we started getting more hardware special. I'm sorry, some extra hardware to be able to handle that part. In this case, Intel adds the extra set of instructions, and we can see how now you can process way more megabytes per second compared to how it was before that. And it's really similar when we use SSL as an example. If you were using SSL 15 years ago, you were Mr. Fancy Pants. Man, you're encrypting your traffic and it needs to get decrypted. Man, I mean, you are adding some overhead. Yet nowadays, if you are not using SSL, the web browser now complains immediately. It is like, hey, this site is not safe. It's not using it. So I just wanted to put some perspective into how things that seemed also slow years ago just keep evolving until they end up becoming a standard. I just wanted to take a few minutes to summarize a little on that. And now the real question, because everyone are into LLMs right now, and can you actually have an LLM working with homomorphic encryption? Short answer is yes. Long answer is it is way more complex than that. And we will see why. So if we, one second, sorry, I need to keep clearing my throat. If we look at the first example that I gave you, and then it seems simple, right? I mean, if you don't have homomorphic encryption, you send your question. Let's use ChatGPT as an example because we all love to use ChatGPT as an example. You send your question, gets encrypted, ChatGPT gets it decrypted, runs its magic. Then it says, this is your answer, it encrypts it, sends it, boom. You're using homomorphic encryption. Well, just add the extra lock, right? Just do it homomorphic. And yeah, I mean, it can be that simple, but it, it's all about the size. It's not as simple as saying I'm sorry, 5 times 3 is 15. You're doing some crazy math on a huge amount of features. We are talking about millions and millions and millions of features that the LLM has. And all of the, how can I say, all of the layers on the neural network that are in there in order to be able to process it properly. And that's a huge amount of operations. I mean, if we just look at a simple example like a vector by vector multiplication or a matrix multiplication, just look at it. I mean, you are pretty much saying on a vector, oh, this times this plus the multiplication of this times that plus, and this is a really small example. If you go into the matrix, it's even worse. Now you are in like the product of this plus the product of that, and many times. Just imagine a multi-layer example. I mean, the chart that I did put at the end, it's cute compared to how crazy it will be for an LLM with all of those millions of features all over the place. And since homomorphic encryption is slow, if you bring it into a scenario where it is that crazy, yeah, I mean, it can do it, but it's gonna take an eternity and it's gonna cost you a lot of money. So that's why I keep saying that, yes, it can be done, but it's not that simple. And I keep saying slow here, slow that, but I never say how slow. Is it 5 times slower, 10 times slower? Sadly, it's worse than that. And depending on the complexity of the operation, because it's not the same to multiply 3 times 4 than having a 12 digits number multiplied by a 15 digits number and then also apply the modular arithmetic to it. And it can be from thousands of times slower to a million times slower. That's a lot. And that's the main problem when it comes to it. But don't worry, you might be thinking, hey, wait, so you're talking about this thing and I'm wasting my time because I cannot use it? It's going to take an eternity? gets better, just bear with me. I need to stop here because maybe you're thinking that, and I don't want you to think that. But yeah, let's focus on how slow is slow for now. So if you multiply two plain text numbers, small integers, it's going to take 1 nanosecond. I mean, you can perform that on your preferred programming language, just add some monitoring there, and boom, it took 1 nanosecond. And, oh, sorry. If you do it in a homomorphic operation, sorry about that again, it can take somewhere between 10 milliseconds to 1 second. Um, 1 second for a single multiplication can be a lot, even if it is a complex one. I mean, it is a multiplication. But if we bring ASICs into the formula, which is related to when I talked about hardware acceleration a few slides ago, now you can actually do it in 0.00001 seconds, which, yeah, it's not as fast as 1 nanosecond, but it's way better than taking an entire second multiplying two numbers. Like, come on. And there is a reason for it to be slow. You might remember when I was talking about the types of homomorphic encryption. We have the partially, the somewhat, and the fully one. So the thing is, in order, do you remember that I said infinite amount of operations for fully homomorphic encryption? The reason is because it's really similar to the somewhat homomorphic encryption. Um, it has a finite number of operations, but it has something called programmable bootstrapping. And what it does is pretty much be able to reset the level of noise to a point where it is able to understand again those values. If we look at it in a really simplified way, we can imagine that every time you perform an operation, it adds some noise. It gets blurry, to call it in some way, like the image that I have here. So you're performing an operation, it gets a little blurry. You keep doing it more and more and more, and it keeps getting more and more blurry until it reaches a point where it might be hard to see what it has, so that it might give you inaccurate results, as I mentioned on the somewhat example. But instead of just saying, hey, I will stop, I can't continue, or just giving you inaccurate data, the PBS, or programmable bootstrapping, it is a process that will reset the noise. It's going to say, yeah, you know what? It is so blurry. It's hard to understand. I don't want to take the risk. I will run the PBS, and boom, you're like as good as new. But this is a complex operation. This is not as simple as saying, yeah, noise equals 0. There we go. I mean, there is a lot of heavy computation to be performed. And because of this, you are doing it many, many, many times based on the complexity of your process, and that adds a lot of slowness. So that's one of the reasons of the slowness. Of course, there are way more technical scenarios and things happening, but we're not gonna get into that. Just wanted to give you some glimpse on some of the reasons behind it. So when we summarize this particular section, which is the LLMs and fully homomorphic encryption like living together, yeah, there are some bad things, and they are obvious. It is fairly slow, so maybe you are not gonna get the performance that you want, and even worse, it is not cost effective. I mean, even if it was super fast and you were getting a kind of expensive monthly bill, who cares? It was fast. Maybe you had a scenario where it works, even by being expensive. But if it's going to be expensive and it's going to be slow, yeah, not really what we're looking for. However, that's not all negatives. As I say here, right, there are modern compression techniques that can reduce the amount of data to be computed. Crypto techniques are getting way better. I mean, just lately we have seen 5 times improvement on that. Plus, there are a lot of research papers, trying to focus on either getting rid of the PBS or just reducing the overhead that it creates. And that will drastically increase the speed of these algorithms. And of course, we have dedicated hardware acceleration, as I mentioned with ASICs, that it's promising at least 1,000 times faster with first generation that will be coming on 2025. But they are supposed to be way, way, way faster by 2028, if I recall correctly. So yeah, maybe the current state is not good enough for LLMs, but that's not that big of a deal because yes, they are good, but LLMs are not everything. I mean, yes, they are amazing. They are not the future. They are where we are right now, and they are only going to get better. But the fact that we still have so many machine learning algorithms that can leverage something like this makes it actually fairly good. Of course, as long as you know what you're doing, right? So do not feel discouraged just because the LLM scenario doesn't look as good as it could be, but see it just as where we could potentially be moving forward in the near future. But still, it's something that can be used in one way or another, maybe for prototyping, maybe for a small product, prototypes. I don't know the extent of things that you might have in mind, but there are many scenarios where it's still feasible in one way or another. And now I keep talking about this, right? Like, oh yeah, homomorphic this, homomorphic that is great, blah, blah, blah. But how do I use it? So what, should I be a cryptographer to understand that and do all the magic? Well, there are libraries that will make your life easier. One's better than others in some aspects. For example, in my personal experience, I did play with Microsoft Seal and with SAMA. I haven't played with IBM's HE-lib, which is homomorphic encryption lib. That HE stands for. What I can tell you, and we are gonna get a little deeper, don't worry, is Microsoft Seal. You need a lot of code just to be able to say, I'm gonna multiply two numbers. 1 times 3, it's equals 3. Boom, you're done. Yeah, 50 lines of code because you need to do all of the setup and all of those crazy things. SAMA, on the other hand, is pretty good, and we're going to look into that one. That's the one that I want to focus, because they are trying to make it accessible not only in such a way that you have the computation there with their resources, but also their libraries that makes it really, really, really simple to leverage, which take us to the homomorphic encryption examples. And I will be relying a lot on SAMA because they are doing some amazing things when it comes to this. So give me a second to get the right screen here. So yeah, it's this one. So yeah, we're on SAMA's page, and it's Hugging Face is where they have their demos and so on, but it's SAMA AI pretty much. So I have 3 examples that I want to focus on when it comes to this, which, by the way, now, you know what? I will say that at the end. So in this particular example, we are doing a credit card approval prediction process, like pretty much based on all of this data, how likely are you to get your credit card approved or declined? And this is a fairly complex scenario because you are not just saying encrypt this, process, decrypt. Now you have 3 different entities. You have your applicant, which is in this case you as a person who wants to know it. You have the bank and the credit bureau. Each one has its own set of data. You as a user have your personal data, the bank has its own, and so on. It gets into the credit scoring agency. Everything is encrypted. It is processing whatever you got. And once it provides the encrypted response, you need all 3 entities, being the bank, the credit bureau, and the applicant, to code decrypt it. And now you get the response. This is not only showing that you can use a homomorphic operation, but it's showing how you can use some type of multi-party computation because each one shares a part of the key so that you're able to perform the final operation. Well, maybe not multi-party. It just has a better name that I just can't remember. Sorry about that. But once we go here, and you know what? I was running this later. Let me refresh so that it's brand new. So, okay. We start by generating the keys. This is really intuitive because it's showing you pretty much how it will be. Even if you're not an expert, you get to understand a little of how it works. So you are pretty much generating the keys, you have the keys, and now you need to fill information. For example, what are you looking for? A car, a property, a mobile phone. I mean, each one is more expensive than the other. So let's go that I want a property. I have 2 children, and my house has 4 bedrooms. My income, let's put something here. And I'm 34. And yeah, just fill the information. I'm married, I'm an engineer, blah, 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 blah. I will encrypt this. And yeah, we have an encrypted representation of let's say, the array of data that we have here. Now, the bank information. How long have I been with the bank in months? Yeah, let's say that I have been, let's be conservative because I want it to be declined. So yeah, 36 months. We encrypt our data for the bank. credit bureau information. I'm employed. Yeah, I'm employed, and I have been less or equal to 2 years. So let's go with this as well. Then we run the evaluation. It's running on the server, and there it is. Do you remember that I told you that I was slow? That wasn't really slow. I mean, because again, when you are on the right context and you know what you're doing with, they do know what they're doing. Um, it gets way better. Now we're gonna receive that encrypted input and we're gonna decrypt it. And yeah, my credit card is highly likely to be denied. And we can also get some extra comments computed to know like, hey, what can you do to get it approved? So it's running, and yeah, it's highly likely to be denied. However, if I have between 2 and 5 years unemployment, it will increase my chances. It doesn't say that it will accept. It will just increase my chances. This is cool because, again, only the ones who own the keys are going to be able to get them together and look at all of this. Now, let's say that I make way more money and that I have been on the bank for way longer and that, yeah, let's say that I have been employed for this long. Let's encrypt again, all of them. We run it again and just look at this. It was 2.11 seconds. Again, yeah, it is slow compared to something doing it on plain text, but that doesn't mean that it's like we're going to be waiting here for 2 hours just to get the computation performed. So now it's highly likely to be approved. And well, there's nothing to provide feedback, right? Because there's no feedback to be provided. So this pretty much is one of the examples. It shows a lot of power because, as I mentioned, we have three different entities providing encrypted data with a derived key, the credit scoring agency looking at all of that without knowing anything about the data. It's gibberish. It's just like a bunch of random characters that once you perform computation give you another set of random characters, and only with the key they will know what it means. And I keep saying this, but that's really, really, really powerful. And just let's run into a more simple example. I mean, that was showing just a lot of the power that it has when it comes to different encryption schemes and how the keys can be used. This one is really similar to the example that I gave you early in the presentation, actually, where you have some symptoms. The server is going to analyze those symptoms and it's going to tell you what potential disease you could have if that's the case. So let's come here, like I have abdominal pain and nausea and maybe some throat irritation. And yeah, let's say that here I have some, yeah, breathless because I don't know many of those words. So let's stick with this. And only those. Yeah, I mean, oh, at least 5 symptoms. Okay. Yeah, let's go with loss of smell. I think that's, yeah, okay. So now we have the data. It's here still, right? We want to do the key generation, encrypting, and so on. We have it here. Here is our vector of symptoms. I like the fact that we can see the plain text and how it looks once it gets encrypted, because if you're familiar with this, it just makes more sense. And now, once we have it, we can send the data. It was sent. We can run the FHE evaluation, fully homomorphic encryption. 0.01 seconds. Told you. It's easy to get pessimistic once you are hearing me say many times, it is slow. But it just depends on the context. It's way slower than plain text operations, but you can still get a decent performance. So let's get the data, let's decrypt, and boom. Oh boy. Yeah, I just picked random symptoms. So apparently you have a 16% of probability of that being a heart attack, a chronic cholestasis. I don't know what that is. And just get the idea. One more time, and I keep saying it. You're getting encrypted data. The system never knows anything about that. It doesn't know anything about your response, and yet you as a user are able to see what the processed data and encrypted values. And the next one will be the really simple one, to be honest. Now, this goes more with file inputs. In this case, it's an image. It is just the ability to say, I will upload an image, I will encrypt it, I will apply a filter over the encrypted image, and once you decrypt it, it will make sense. Again, homomorphic operations all the way long. So let's pick this cat. Let's say that I want black and white because that was really easy to see. We generate keys. We always generate keys. We encrypt the image. There it is, our encrypted version of it. We send the encrypted values to the server. I think funny thing is, I think it takes longer to upload it than to run because it took like 5 seconds to upload it. Let's see how long it takes to run it. Okay, 4 seconds. There you have it. Now we receive the encrypted image. And that's what we get because again, we send something encrypted gets processed, and we need the key to see the real value. Sorry, and once we decrypt, there it is. The same image, now with a filter that it was able to understand only with our key. The server doesn't know about the cat, doesn't know about the black and white cat, just knows about some random bytes being there. And something really powerful about SAMA, this will be almost the end because we're running out of time and I think that there is a QA as well, is that, as I was saying, Microsoft Seal, it's a lot of code. It's like all of this set up just to do a basic multiplication. If you want to do some regression, classification, whatever you want to do, it will only get crazier. But SAMA has its own library that pretty much extends scikit-learn from Python. You might be familiar with it. And it makes it as simple as using the functions that you already have in there, like the fit, predict, and so on. But it adds an extra parameter, being the FHE, and what you want to do with it. Of course, provided the keys and so on. But it's make it so transparent because now you can just leverage what you already know, add some extra things here and there, and of course, your data being compatible and so on. And now you have homomorphic encryption in place. And all of this is using SAMA's libraries. I mean, it is SAMA's page. But I think that this is a really powerful source if you want to prototype, play with it, get more familiar with machine learning. I still think that Microsoft Seal is really good to give you an initial insight so that you can say, I have really basic arithmetic operations and multiplication, addition. I want to see how slow it is by just doing it without any optimization. And you will see how crazy it gets. I mean, I had an example that I played with that it was taking like 1 minute to multiply some values many times on a loop. So that's a lot. I think that it gives you to get context, to understand what it is. And once you jump into SAMA's libraries, you come here with a better understanding instead of being your the first time that you're exposed to this type of things. So with that said, let's get back into the presentation just for the final slide. Oh boy, just give me a second here. Okay, so now let's wrap this, right? First thing is, should I start using this in my projects? Short answer is no, maybe no. I already said why, right? Because there are many things to take into consideration. You have all of the performance, you have the potential slowness. You really need to know what you're doing. You really need to know your use case scenario because, I mean, yeah, it makes sense to encrypt financial information, maybe medical records and things like that. Does it make sense to do this for something really simple that is not using data that really needs that overhead just to keep it safe? Maybe not. Plus, you need a lot of understanding of what's happening. It's good to know that it's there. It's good to have companies like SAMA that are making things easier for people who are not cryptographers. Because, I mean, I'm a developer. I'm not a cryptographer yet. It gives me enough understanding to be able to know what's happening, to be able to use it and get familiar with it. And the main thing is it's in there to prototype, to play with it, to get familiar. Just this is not a hype. And things are definitely taking a similar path to this. Maybe the AI part is not going to be the first one to do it, right? It's one of the most complex scenarios. But it's definitely becoming a thing. It has been there for many years. We are getting better computational resources to start leveraging it properly, something that could not be done on the 80s when this was first discovered. So just do not feel like you listen to something just to get to a tool that you cannot use, because that's not what it means. It just means that you need to be aware of this. You need to know where it goes. You need to know what it does and potential use cases where it can be useful. And sooner than you expect, it will be all over the place. Honestly, I mean, Microsoft is on it, IBM is on it. There are many companies investing on hardware acceleration for it because they want it. So if I go back into this and I stop just talking about everything except for what I have on the presentation, yeah, maybe you should not use it on your projects yet. There's the CPU overhead, there is the slowness, there is the expertise that you need to have to understand what are you doing. However, it is functional. Companies are paying attention to it. They want to start taking this path. And it's good to know that it exists. Again, now you can think about this as a possibility once you are maybe in a project with a really complex scenario, or maybe you want to design your own product and you want to keep security as your main thing. That's what Sama is doing. They are offering libraries, but they are also selling services. So there you have it. But yeah, I mean, that will be all from my side. Hopefully you got something useful from this. Hopefully you learned something that you did not knew about, but that will be all. So thank you very much for sticking with me for almost an hour. And I think that I will let Adi just add anything he needs to add. I mean, I think that there is a Q&A, so let's go with that.
Thank you, Arnoldo. I hope now I will keep my internet connection going. Thank you everyone for coming. I don't see any questions in the chat, but maybe someone has something to ask right now. So if you have questions, here are your few minutes to ask Arnoldo if there is something you are more curious about or just want to comment on.
I mean, if there are no questions, it means that I was really clear, right?
You were just
Perfect.
speaking my language. If there are no questions, the lecture was great. That's how we also rate it here at AVSL. So once again, thank you everyone for joining us. I know that there is another event going on in Sarajevo right now at Authority Partners. So I don't mind if we finish earlier. Once again, Arnoldo, it was really a pleasure having you. For those who couldn't join us today, the recording will be available on the YouTube channel in a few days, and we'll inform the whole community so they can rewatch it. And if there are any questions after the recording, of course, we invite everyone who is listening to this after being published on YouTube, contact us on our official social media or email addresses. If you have some questions and comments, we'll make sure that Arnoldo gets them and answers you.
Awesome. Thank you very much, all.
Thank you once again.
Thank
and
you.
see
Great
you on the
job.
next opportunity.